All right, how's it going, everybody? We are here. I'm making this video on Friday, April 16th. Today, we're going to talk about section 9.4, where we're going to introduce vectors. It's going to be kind of our introduction to our last topic of the semester here, or we still might touch on one other thing here, but I'm looking for our conclusion of this semester to be to look at vectors, matrices, and matrix transformations. So it's definitely possible that you maybe have seen some matrix operations in an algebra class. We're going to look at some slightly different uses of matrices as sort of our goal for our last couple of weeks. So this week, since we had our section 9.3 already this week, section 9.4 will just be our little introduction to vectors. Starting out next week, we'll look at the dot product in section 9.5, and then I'll create a little bit of sort of my own content that doesn't the book might have some things that are matching up with what we're looking at, but a little bit different location in the book. So in any event, we're going to look at a couple other matrix operations that we can do, see how these things are related to our trigonometric ideas that we've been looking at this semester here. The good news is that today, as is always the case, sometimes when you start a kind of a brand new topic like vectors and matrices, it definitely might be the case that it's unfamiliar to you, which makes it a little bit challenging. But it's also the case that day one of any new topic, we're never talking about the hardest parts of that topic, right? So today we're going to get lots of notation, lots of definitions, stuff like that. Our math will get a little bit more complicated next week, but I don't think that you're going to be too blown away by what we see today. That being said, we will wrap up with an example that's slightly challenging, but doesn't involve anything more difficult than kind of some of the trig that we were doing at like the beginning of chapter 7. So it's really not going to be that crazy here. So again, we're talking about vectors here today, and so what we want to do to start is define what is a vector. And this is one of those things where I can't really define what a vector is without comparing it to another idea called a scalar. So in general, these are kind of some comparative statements that I've made right here. To define a vector, we compare it to a scalar. A scalar is a number that's really just a number, right? It's just a magnitude, it's just an amount. So if I'm talking about a scalar here, some examples might be that I might say $5, there's a scalar. It's just an amount. It certainly has a unit attached to it, but it's just an amount, right? It could be 6 feet is another scalar. It could be 90 miles per hour. These are all scalars because they're all just describing amounts of something. You should notice that this one is a dollar amount. This is a measurement of feet. This is a rate right there, miles per hour, right? But they're all just measuring amounts. The difference between a scalar and a vector is that a vector also has a direction that is indicated in association with the amount. So in this case here, we might say something like 300 miles northwest or something like that. That's got a direction that is directly tied to the quantity that we're interested in, right? 300 miles northwest. All right, so the essential distinction between a scalar and a vector is that scalars are really like every number that you've ever dealt with in your pretty much your entire life. It's just describing an amount. Vectors always have direction being tied to them, right? So vectors always have both magnitude and direction needing to be described. Scalars, when we graph them as points or as locations, right? So when we graph a scalar, we might be on like a number line, right? And I might say, oh, it's that location right there. It's like x equals 3 or something like that. Or maybe we're in two-dimensional space and we come over to some location over here and we're maybe sitting there at like a -2, 1. Those are both scalar locations right there. Vectors, on the other hand, because they're indicating an amount and a direction, are graphed as directed line segments. So instead, we might be out here in a plane and we might have a scalar that is indicating to us a direction or an amount and a direction in which we're traveling in that amount right there. So vectors always are graphed as a ray, right? A directed line segment. Another word for this is just a ray. It has a obvious starting location and it has an arrow indicating the direction of the motion that we're going at here. If we were looking at the 300 miles northwest, 300 miles northwest might be like that vector right there, where the length of the vector would be 300, the direction of the vector would be northwest. So I tried to graph that as like our 45-degree angle north and west right there, right? 135 degrees. Scalars tell us locations in space, like we graphed up above. Vectors tell us how to move in space, right? So when we look at the scalar, it is telling us where we are. Vectors tell us how to move. So vectors are instruction sets. I sort of like to think about scalars as being like a nouns, like being nouns, and vectors are like the verb equivalent of the noun right there. Scalars say, I am at the grocery store. Vectors tell you instructions as to how to get to the grocery store. They're very obviously closely related. They are obviously also not exactly the same thing right there, right? So scalars are where you are. Vectors are how to get there. It's the instructions that would cause you to arrive at that equivalent location, right? So again, lots of close relationships between scalars and vectors, but kind of very distinct ideas here. And again, I really like sort of the parts of speech distinction right here. Vectors are action. Scalars are descriptions a little bit more, right? So notation for vectors. It turns out there's a whole bunch of different ways that we can notate a vector. We're going to look at three essential ones today. The one consistency between all of them is that our vectors are always notated with a little arrow above the name of the vector. So just like x and y are like the most commonly used variables whenever we're doing algebra, v, the vector v, is our typical most generic vector. U and V are the ones that you'll end up seeing a lot. And what you can see is it's got this little arrow hat. In fact, if you're looking at your notation in Microsoft Word, I'm pretty sure it refers to that as a harpoon because it only has one of the two things on. It's not like a double, it's not an arrow like this. It's an arrow like this right there. So it's not that guy, it is that guy right there. So the harpoon rather than the arrow, but whatever. I don't really care too much about that. The point is, if you don't put that little symbol above your descriptor of the vector, then we don't know that thing's a vector. So this is important notationally, that every time you're notating a vector, it always gets the little arrow symbol above it to express that we're talking about a vector. And you can see that one of our notations that we can use for a vector is that you're used to points in space, like the point P being located at AB. We can instead talk about the vector V. And notice here we're using these little like cornered brackets right there for AB. It's an instruction set. It says go A units to the left or right and go B units up or down. Obviously, those are the instructions that would take us to the location AB if we started at 0, 0. So again, very, very, very closely related right here, but one is a location, one is an instruction set, and those are definitely two different things right there. So let's look at a couple examples. Let's notate some things. Let's look at converting between the notations here. And all you're going to see is some of the basics of trig that we've seen before here. So these two phrases are both phrases that are describing vectors to me. So this first one here, go up 3 and down 4, I can write this as the vector v being saying go 3 units to the right and go 4 units down. Notice that down is what we typically consider to be one of our negative directions, and so I think notating this as 3, -4 is a good vector description right there. Go up 3, or sorry, it would be a good vector description if that wasn't up. I meant that to be right 3, not up 3. Go right 3 and go down 4. Now this is very, very similar to us giving XY coordinate directions, or XY coordinate locations, but you should notice that this is a set of instructions. Another really important thing to notice here is that this doesn't exactly tell us a starting point from where we're moving. This doesn't say from the origin, go right 3 and down 4. So vectors, you should notice, are independent of starting position. They are not dependent on a location. They are instructions as to how to move, but they don't say where to move from. So let's say, notice vectors are independent of location. They're just instructions as to how to move. It doesn't say from where. Now, another completely reasonable vector for us to indicate here is this one that's sitting next to it, go 5 miles at 60 degrees north of west. This is an amount, 5 miles, and a direction, 60 degrees north of, or west of north, and so therefore this does represent a vector. Unfortunately, it doesn't seem obvious to me how I can exactly state it in this vector format right here, but fortunately it's not terribly uncommon to literally just write this vector as we see it right here. 5 miles at, now, I don't think 60 degrees is an appropriate descriptor right here. Why not 60 degrees west of north? What is 60 degrees west of north actually indicating to us here? If this is our east and our north and our west and our south, then 60 degrees west of north should actually be like this guy right here, right? Where there's our 60 degrees west of north. So my question to you is, what might be a slightly better angle for us to refer to this as so that we don't have to indicate our wests and our norths and stuff like that? We typically think of, east as being sort of like our, in terms of our trigonometry, right? We consider this to be our 0 degree angle right here. So maybe we want to think about this as being 90 plus another 60 to make 150. So maybe I would call this guy 5 miles at uh, 150 degrees right there. So that might be my good description of this vector here. 5 miles at 150 degrees. We know that a 150 degree angle is that angle that's pointing out into the second quadrant, which would be 60 degrees rotated beyond our upper 90 right there, which we're thinking of as north. So recognize that you can interpret cardinal directions here in terms of angles and kind of maybe reconvert them back into an angle in standard form. And again, it's called standard form for a reason because it is standardized so that everybody actually knows what you're talking about right there. I think it's pretty clunky to include phrasing like west of north in our vector descriptions, so that's why I typically will convert any angle that I'm given and its associated cardinal directions into an angle in standard form. Or I should say angle measured from standard position, which is the positive x-axis. Now, this is two ways that we can indicate a vector. What I want to look at is the third one that ends up being the one that is most commonly used. I think that these two make a whole bunch of sense right here. It turns out there's going to be one that's going to be slightly more practical for us to do math with, but we are going to see this sort of polar type version right over here. And again, you should notice this is literally basically just rectangular versus polar form right here. Maybe that's kind of worth stating real quick here. So this is kind of really following exactly along with the discussion that we've been having in the last week, which is that there's sort of this XY coordinate description and there's this R theta description. And we've got that XY in the left one, we've got that R and theta in the second example that are right here. So this looks to me like our polar or uh, our vector version of the rectangular coordinates versus polar coordinates here. So let's look at a third notational option here and then convert between all three of these guys right here. So unit vectors are what are most typically used to describe vectors in general. The most basic units of movement in the plane, the most basic way I could describe to you some motion is talking about steps that are 1 unit moving horizontally or 1 unit moving vertically. So not necessarily going 3 units, not traveling at 60 degree angles. I'm talking about traveling 1 unit at a time in exactly the direction of our two axes, right? So in general, we refer to the I and J vectors as our basis unit vectors for 2 dimensions. I is going to be the vector that moves us 1 unit to the right. J is going to be the vector that moves us 1 unit up, right? So graphing these two guys, get a color out here, we get that this is our I vector, put my hat on it, and that this is our J vector. They're each the vectors move right one and move up one. I hat and J hat right there. What we typically do then is we can write constant multiples of these vectors here to express the directions of motion that we are looking to travel. So our first vector up above is we had our vector v was equal to, we had this as the vector 3, -4. Well, we can think to ourselves, going 3 units to the right is really like going 1 unit to the right 3 times. Therefore, when I go to write my vector here in component form using my i's and j's, it looks like this 3 right here could be expressed as 3i because that says go to the right 3 units. What else do you want to do if you're going to follow this instruction set right here? We also need to go down 4. So I think here I could also say something like -4j. So this is my instruction sets here that says go right 3 units, do 3 steps of going to the right, and then undo 4 steps of going up. Undoing 4 steps of going up should do 4 steps of going down right there. So this would be our component form vector that's equivalent. I's are always describing horizontal motion. I is the vector that goes 1 unit to the right. J is the vector that goes 1 unit up. And so we can express the vector 3, -4 in component form here with the i's and the j's. Now that one's the pretty easy one because we literally just stuck an I and a J on the 2 components that we had right there and called it good. The next one that we have here is a little bit less obvious, right? We've got our 5 miles at 150 degrees. So what it looks like to me is that it looks like our first notation that we saw with these brackets is very, very closely related to our rectangular form. And our rectangular form seems to be very, very closely related to our component form right here, our i's and our j's. So it seems to me like we sort of want to convert our polar form vector into a rectangular form vector. So what I am picturing here is we've got our vector 5 miles at 150 degrees. Looks like that vector right there. And what I want to know is where would we end up? If we started at the origin, where would we end if we were to follow the instructions of that vector? Well, I can see that it has a radius of 5 and an angle of 150 degrees. And so what I think that I can do for myself here is I think I can just use my basic polar conversions to convert into rectangular form to find our information. So I think that I'm going to get my vector here to be my x information, and that's how much stuff I'm going to do in the I, or that's how many sort of copies of the I step I'm going to do, where I says go to the right one. And then we can do our y information, our sine theta, and that is associated with our j vector, our vertical vector right there, our vertical unit vector. So in this case here, it seems like we're going to be getting 150, or sorry, 5 times cosine of 150. I plus 5 sine 150 j. And what is that going to lead us to here? This should be, oh, it's gonna get mad at me now, isn't it? It is? Okay. Let's go ahead and fix this here. Oh man, it's gonna mess up my nice spacing that I had down there. That's okay. So when I do this here, cosine of 150, I can see that it's going to be negative. It looks like our horizontal component here is more than our vertical component, so I think that's going to be my root 3 over 2. So I think that I'm getting here that this should be 5 times root 3 over 2i. And a negative, we're going to the left right there, right? And that should be our I vector here, not our j. And then plus, this should be our 5, and sine of 150 is just going to be 5 halves. So it looks like I've managed to convert this thing now into component form. The reason that component form is really good is because it makes it easier to do math between vectors. When we're in component form. And that's what we're going to look at next here. All right, so we converted each of these into their component form with the i's and the j's. So very, very typical that when you work with vectors, you'll see lots of i's and j's floating around everywhere. Those are just indicating which direction we are expressing our motion in. I is always to the right by 1 unit, j is always up by 1 unit. And so by taking constant multiples of these and perhaps some negatives, we're expressing the fact that you might want to do more than one step of that, less than one step of that, stuff like that. It's certainly the case that we could, if we wanted to, get decimals for those. I don't think that's really that important right there here. We've got our component form of this vector here. So we've converted either from our bracket form or our polar form into our component form. And again, what we're going to see is that component form is going to be really nice for doing some math here. So what we want to look at now is doing some operations between vectors. What we'd like to do is get a good idea as to how to perform our basic arithmetic operations with vectors. We're going to look at addition, subtraction, negation, and constant multiples here. What we're going to see also is that you should notice that the things that are missing from that list are things like multiplication, division, and exponentiation. And what we're going to see is that those operations are not as well defined with vectors as they are with scalars. We're going to need to go into matrix land to talk about what it means to do this type of multiplication, or at least the dot product next week, will get us to start to think about one of the types of multiplication that we could possibly do. There are actually several different multiplications that are defined for vectors and matrices here. Those are kind of the things that we'll be talking about over the course of the next week. So we're just going to look at the basics here today. These four things: addition, subtraction, negation, and constant multiples of vectors. And a very, very important thing is that every time that you're working with vectors here, you should be able to graph exactly the arithmetic that we're discussing here. It's really, really helpful to be able to visualize these things in a coordinate grid. So you'll see in your homework, there's going to be plenty of questions that are going to ask you to do vector graphing associated with operations between vectors. That's a really important thing. We got to be able to visualize these things, and you'll see some good examples as to why in the problems that we'll do, or examples at the end here. So let me fix my spacing one more time here. Okay, that'll be good right there. All right, so in this example, I'm giving you three vectors that we're going to use, and let's go ahead and do some operations between these vectors here. So I'm giving you the vectors 1, 3, 4, 2, and negative 3, 0. One thing I'm thinking to myself right away is I have other ways to describe these vectors, right? We've got our component form, so I might say that u is the vector I plus 3j. I might say that the vector v is 4i plus 2j. And we might say that the vector w is the vector negative 3i, right? There is no j component on that w vector right here. Somehow it escaped my memory that we literally just talked about imaginary numbers, which also use the letter I. Unfortunately, I guess that is a little bit of I confusion right there, but fortunately for vectors, I will always get a hat on top of it, and we'll never talk about the imaginary vector direction here. So our good news is that there shouldn't be any I confusion. If it's got a little vector hat on top, it's a vector. If it doesn't, then it's an imaginary number. So let's go ahead and first things first, let's draw all three of these vectors. One thing that's really, really important here that you should notice is that I created graphs here for drawing that don't indicate any origin or axes right here. Remember that vectors are instruction sets. This first vector says things like go to the right one and go up 3. It doesn't say from where, it just says to do that. So what that means is that you could do that from any location in space. Anywhere that you would put this vector is fine, as long as the steps that it does are the right one and up 3. So, for example, starting from this location right here, I could go right 1 and I could go up 3, and therefore my first vector u should be this vector that's right here. So there's my u vector. That is a vector that went right 1 and up 3. My v vector says go right 4 and up 2, so I could go right 4 and up 2. So there's my end point right there. There's v. And finally, my w vector says go left 3. So there's a w vector right there. So again, it doesn't matter where in space these are at all. All that matters is that we're following the instruction set associated with the motion tied to these vectors right here. So what we're a bit more interested in here is looking at these operations between the two of them. So to graph uv, what I want to say is do u, then do v. Do the instruction set for u, followed by the instruction set for v. So what I'm going to do is I'm going to start at some location here, and I'm going to do the vector u. So there's a copy of the vector u. I'm going to go right 1 and up 3. Then from here, I'm going to, so we're doing the action of u, and we're doing the action of v. So I've done the action of u. Now from this location, I'd like to do the action of v, which is to go right 4 and up 2. So that should bring me to this location over here. So here, what I've done is I've done u, I've done v, and it now looks like I can say that my final vector right here, let me get a new color, is going to be this guy. Hey, I can't believe how straight of a line I just drew right there. This is our u plus v right there. We did the instruction set u followed by the instruction set v. A good thing for us to notice right here is that we can just do the math with these guys right here. U plus v. I always like to picture these being in component form here. So this would be I plus 3j plus 4i plus 2j. And you should notice here that the convenient thing about these i's and j's is they help us keep our like terms together. This says to me, in total, it looks like we're doing a grand total of 5 units to the right because I've got 5i. Similarly, it looks like we're going 5 units up because I've got 5j. Right? This should be my u plus v vector. And if we go look over here, we can see we did in fact go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we did exactly go 5 units up, or 5 units right, and 5 units up to achieve the overall action associated with u plus v. Right? But again, the u plus v vector is the one that encompasses the very, very beginning to the very, very end. A lot of times in textbooks, I see the phrasing of tip to tail, which means that when you're doing addition of vectors, you're always just sort of attaching them one to the other. The end of one is the beginning of the next. The tip of one is the tail of the next right there. So let's look at some more of these mathematical operations in graphical form here. So same exact 3 vectors, I just copied them again. Let's go ahead and look at our scalar multiples over here. I think, let's see, I got some room, right? Yes. Let me give myself a smidge more room right here. Again, I like to think about these guys as being in their component form, so I'm going to rewrite these again like that. All right, so we've got our component form vectors right here. What I'd like to graph over here is a negation and some constant multiples of the vectors that we're interested in here. So for all of these, I'm going to draw also all of the originals on the graph again. So I'm going to start by graphing u, and what u is telling me to do is u is telling me to go to the right 1 and up 3. Therefore, the negative of that instruction should just be its opposite, right? So negative u is going to be negative I minus 3j. So this is going to be, therefore, the vector that looks like this guy. It's going to say go to the left 1 and go down 3. This is negative u right there. And that shouldn't be a mu. That should be a u. All right, so u's are just doing the same type of action, but the opposite direction. This is sort of like the go to the grocery store versus come home from the grocery store thing. The next vector that I'm talking about here is half of v. Well, let's draw the entirety of v first. So v is saying go to the right 4 and up 2. So maybe we'll start right here and go right 4 and up 2. So there's all of v. So to do only 1/2 of v is only going to follow half of this instruction. So hopefully you can kind of see that just doing the first half of this line and ending right here, that would be a good half of v right there. So maybe I'll even just do it just like this. There's half of v. We literally just did v for only half as long. Right? And you should notice here that similarly, algebraically, half of v just says take half of each of your 2 components. And that's exactly what we did. 2 to the right and up 1 is exactly what the half of v ended up looking like right there. Finally, we're interested in 2w, and we can see that w is the vector that said go to the left by 3. So there's our original w vector. Well, 2w just says do w's instruction twice. And so we can picture for ourselves that 2w, therefore, is going to say go to the left by a grand total of 6 units right there. And it's really like all we did was we just stuck that onto itself right there. So notice that 2w equals certainly equals negative 6i. But notice that we could have thought about this as w plus w. So it's sort of like when we did our addition a moment ago. It's like I did w once to get to the end of the vector, then I did w a second time. And so the grand total vector was the very, very beginning to the very, very end, which was the 6-unit long vector that we had right there. So this is nice and easy right here. Constant multiples and negatives are kind of doing exactly what you think that they're doing, and we can always use the component form algebraically to help ourselves be convinced that we have graphed the correct thing. Now let's look at our slightly more difficult ones, which is subtraction, and then a little bit more of a difficult addition right here. And let's go ahead and do this graphically first, and then let's see if the graph matches up with the math that we're thinking here. So a really important thing every time I'm doing subtraction is I really try to not think about this as subtraction. I like to think about this as W adding the negative version of V. Rather than actually doing subtraction, I like to think about addition of a negative, because addition of vectors is really, really clear. Like we saw before, you just do the next vector from the beginning of your first, or from the end of your first. So it looks like we want to start by doing W. So I'm going to draw what they are here. So here's W. V looks like the 4, 2 vector. So V is our vector that does this. But what I want to use is the negative of that, right? So what I'm more interested in is this guy, the negative V vector. So now when I'm thinking about W plus negative V, I know that I first want to do what W tells me to do. Then I want to continue on from that in the direction of what negative V tells me to do. So to get our answer over here, I guess I'll do this one in purple like I did the math over here. I'm going to do our instruction set for W, which says go left 3. So there's our W vector. From here, I'm going to go ahead and perform the negative V vector, which is going to tell me to go down 2, left 4. So there's the negative V vector. And so it seems to me like, now let me get another color here. Like this should be our W minus V vector right here, that guy in blue. All right. And we can check this out mathematically over here by just doing our little bit of addition or subtraction, however you want to think about it right here. Our W vector was the negative 3i vector minus the V vector, which was the 4i 2j. That should be to me negative 3i minus 4i minus 2j. And that should be giving me negative 7i minus 2j. And we can, in fact, see here that we did go 1, 2, 3, 4, 5, 6, 7 units left and 2 units down. So it looks like that is in total agreement with what we managed to graph right here. So it is often the case that when I'm graphing vectors, I'll kind of graph the things that I need on the side and then use them to assemble the operations that I'm actually doing in space over here, right? So this is sort of like my showing my work. And this is actually assembling the components that I have worked to create. And we can also confirm that these things are going to happen algebraically here, since we're actually given these like measured right here. I think there's going to be a couple that you're going to see in the homework where they don't actually tell you what the actual vectors are. They just say, hey, look, we graphed U and V for you. You graph U plus 2V or something like that. And then in that case, you can't do the counting or the arithmetic up top. All you can do is do the graphical steps of connecting them together to perform the operations one after another. So as our final one right here, I'm going to go ahead and attempt to graph 2v minus 3w plus minus 3u plus w here. And so let's put all of our pieces together. I'm going to start kind of the same way right here. I'm going to graph all 3 of our things that we want to know about here. So there's our u vector. Here's our v vector. Man, my straight lines are actually really good today. I'm impressed by this. And then we get our W vector. So let's go ahead and see if we can graph this guy right here. I want to do 2 steps of v. Then I want to go backwards 3 steps of u. And then we're going to go forwards 1 step of w. So I don't really know where the best place for me to start is on this guy. I'm afraid I'm going to like fall off of my graph right here. It looks like I need to start by going 2 copies of v. So let's see. So I'm going to start from right here. I'm kind of guessing that that's going to be, I just don't want to fall off the edge of my grid over here. So I'm going to start by doing uh, 2Vs. So I'm going to do 1V. It's going to take me from here to here. So there's a V. And now I need to do another V. So I've done 2V. Now I'd like to subtract off 3U's. So I'm going to do U backwards 3 times. So I'm going to do a negative U, a negative U, and a negative U. Finally, I'm going to add on a W, and W says go 3 to the left. So all I've done is just tracked a whole bunch of stuff around here, right? We just did all the instruction sets, 2V's, negative 3U's, and 1W. And it looks like our total resulting vector should be whatever that guy in purple is right there. This should be our 2V minus 3U plus W. You should notice here in this case, this is sort of us saying, listen, man, if you're just trying to go from here to being down here, you don't need to go take this crazy path. We could instead just do the one simplified path that would take us directly there. So this is the solution in purple right here. If I said to you to graph this, this is the one vector that represents 2v minus 3u plus w. And I do think it's worth kind of seeing that this works out algebraically over here as well. This should be 2u That's 2i plus 3j minus 4i plus 2j plus negative 3i. And when I do this arithmetic here, again, I'm going to go ahead and expand. So I'm going to get a 2i plus 6j minus 12i minus 6j minus 3i. And again, the convenient thing about being in component form is that it's easy for you to combine like terms by just keeping the I stuff together and the j stuff together. So what I stuff do I have? 2 of them and negative 12 of them. That together makes negative 10. And then a negative 3 for the I right here. Did I do my... Oh, I see what, okay, sorry. I'm realizing that this isn't working out to be my purple vector, but that's, notice that this is, I was thinking that this was in the order UVW, but it's in the order VUW. So I've got my arithmetic a little bit wrong right here. Let me back up 1 step. I've got these backwards. That's what it is. Let me swap those. So this should be 2V. So this is our 4I plus 2J. This is U, so this should be our I plus 3j. Now I can go ahead and get my 8i plus 4j minus 3i minus 9j minus 3i. And again, so now back to what I was saying. Now we're just grouping up the i's and the j's, right? So how much I stuff do I have? 8 minus 3 is 5. Minus 3 is 2i. So that says overall you're going to go 2 to the right. For my j components, it looks like I have 4 minus 9, and that's it. So it looks like I'm going to go 5 down. So it looks like this should be the same thing as the purple vector that we just got a bit ago. And we can see that we did, in fact, go 2 to the right and 5 down right there. So graphically, we can assemble our solutions here rather than actually doing any of the arithmetic. So again, it's really, really important that we can deal with vectors graphically. If we can't draw pictures associated with these things, then it makes all of our application problems associated with them much, much tougher. And so it's important for us to really see like kind of how we're assembling these operations graphically here. There's always a strong graphical tie to all of our vector things. And again, this is a promise. Vector math gets really, really hard if you can't draw the picture that represents the operation that you're doing. So these types of things, while they do seem really basic right now, and I know that you guys could just do the math on the right, these graphs end up being the thing that actually are going to make problems possible for you in the future when you go take physics and go take calculus and all that good stuff out there. So one of the things that makes vectors very useful in applications is their ability to decompose angular information into its perpendicular components. And let's go talk about what that actually means to us up here. A minute ago, we looked at this sort of like polar form version, right? There's tons and tons of situations in physics and in calculus where with the information that we've been provided is information about perhaps a force being applied in some direction. And that direction might not be totally horizontal or totally vertical, right? It might be a force applied in some angular direction. What we might then be interested in is if I apply a force in some angled direction, how much force did I really apply horizontally and how much force am I really applying vertically? And I'm thinking about things like if you're going to push on a box at an angle like this, what I know is that I'm not going to lift the box off the ground. So the vertical component of my force here is wasted because I am pushing up a little bit. I am also pushing to the right a little bit, and I know that's really the only force that's actually going to go into pushing the box. So what I could do here is I could find just the horizontal component of this force right here. That's all the force that's actually going to get applied to moving this box to the right over here. The upward force, since I'm not lifting the box off the ground, is essentially going to end up getting wasted. And so what you know is that if you go to push on a box any direction other than completely perpendicular, then you're wasting some of the force of your push right there, right? If you try to push like at an 80-degree angle on a box to get it to move to the right, then you're going to have to push really, really hard to get the box just to move little bits to the right out there. So kind of breaking down angular directional things into their perpendicular components, their I and J components, it's why we call it component form, is a very practical thing to do to help kind of work out how much of the effort is in the direction that we're thinking. So let's go ahead and look at a very specific example of this guy right here. And then let me just bump this one to the next page here. We're not going to need all this room, but this one will need its own page right there. So our example here, our first, so we're going to do kind of like an easy vector application problem and then a challenging one at the end right here. A ball is thrown at a speed of 25 feet per second at an angle of 30 degrees. If the ball is in the air for 4 seconds, how far away is it before it hits the ground? So what I would like to do first is recognize that our vector of interest here was, or excuse me, that the information that was given to us was a vector. It's not just a number, 25 feet per second. It's a number with a direction. So that's a vector right here. So it looks like the vector of interest, V, is 25 feet per second at an angle of 30 degrees. So that is the vector that was told to us. Now, I can graph a vector that does something like that, right? There's my 30-degree angle vector, and this is 25 feet per second. Now, what we're interested in a way is how far away is the ball when it hits the ground? Notice that when we measure how far away a ball is when it hits the ground, it's always an x measurement. It's always a horizontal component. So the deal is this. I don't really care that this ball is going to do some up and some down. That's not my thing of interest. I'm not asking the question, how high up in the air eventually did the ball get to? The question that I'm asking is how far away horizontally from me did the ball end up when it hit the ground? So what that says to me is that even though I knew we threw this ball at 25 feet per second at an angle of 30 degrees, what I'm much more interested in is how much of this motion is in the x direction. Now, I just said an important kind of wrong thing right there. I said how much of this is, well, I said how much of this motion or distance is in the x direction, but we were given a velocity vector right here. So maybe let's ask how much of this velocity is in the x direction. Well, let's go ahead and find that information here, right? So what I'm going to do is I'm going to redraw this vector here, and I'm just going to call it vector v. And what we want to think to ourselves is that we should be able to identify the x component of that vector v and the y component of that vector v. So I'm going to call that v sub x and v sub y. And the good news for us is that we know that this is a 30-degree angle that we're looking at right here. Right? So it looks like there's perhaps a right triangle that's going to help us figure this guy out right here. Right? So what it seems to me is that we should be able to decompose this thing to find v sub x. And what I know I can do with v sub x is I can just use my polar to rectangular format, right? This is sort of like our r information, and this is like our theta information, and we are interested in finding our x and our y information. So it seems like our v sub x should be just the total amount v, or excuse me, I should say the magnitude of v. So I'm going to use some little bit new notation right here. I don't know why we use double sticks in the indication of magnitude for vectors over here. This is just like when we use the single stick for absolute value for the magnitude of an imaginary number. Um, but slightly unfortunately, it's a double stick right there. So this is going to be 25 feet per second times cosine of 30. What is cosine of 30? We know cosine of 30 degrees is going to be our root 3 over 2. And we know that that is occurring in the I direction. Very similarly, we could find the y component right here. In fact, let me get a little more space in here because I want to write down my decimal approximation for that. So I'm going to write v sub, I'll go to my calculator in 1 second right there, and we'll write our v sub x decimal. Similarly, we'll get our v sub y component right here, which is going to be the magnitude of v overall times the cosine, or times the sine of 30 degrees. We know that we're just doing our conversions between rectangular and polar here to get our individual components. Sine of 30 is just going to be 1/2, so we're just going to get 25 times 1/2 j. So what it seems like is really happening here, so let's go ahead and get our decimals for each of these guys here. V sub, gosh, I keep on writing that x. V sub y. V sub y. I'm going to go to my calculator here, and I'm going to do my arithmetic. I am seeing that I want to do square root of 3 divided by 2 times 25 is the total length of that vector. And I'm getting 21.65 for v sub x. Oops, that's an I, not a j. Man, I'm getting my x's and y's and i's and j's backwards all day here. And our v sub y, I can do that one. 25 divided by 2 is going to be 12.5 j. So it seems like our overall vector here is our vector component x plus our vector component y, which in our case here is the 21.65i plus the 12.5j. So interpreting this, what this says to me is this. When you throw a ball, and if your throw speed is exactly 25 feet per second, if you throw it at an angle, then what you should think to yourself is the ball is not moving forward at 25 feet per second. It's moving like up into the air at 25 feet per second. So some of its motion is upwards, some of its motion is horizontal, right? So we've got a vertical component of motion and a horizontal component of motion. Based on the fact that it was a 30-degree angle, we should see that we're going to get a small amount of our motion is vertical. So what this says to me is that the ball is moving up at 12.5 feet per second. The ball is moving to the right at 21.65 feet per second. All right, so let's make these statements here. So we have decomposed the vector that was given in polar form into being in component form. And the thing that helps us that this helps us do now is now we can talk about things like the ball going up and the ball going down, the ball going left and the ball going right. We can talk about just the horizontal and vertical components separately here. So a couple of things. One, We were told that the ball is going to be in the air for 4 total seconds. Well, if the ball is going to spend the equal amount of time going up as it goes down, it must have been going up for only 2 seconds. And so I can see things like the maximum height of this ball was probably 25 feet because it went 12.5 feet per second for 2 seconds. Right? What we were interested in is the horizontal motion associated with this ball. And so what I can see is that this ball, because it was thrown at 25 feet per second, but that was not its horizontal speed. That was its angular speed. What we want to see is how much of that 25 feet per second was in the horizontal direction. And by multiplying it by cosine 30, we found that 21.65 feet per second was the component of it in the horizontal direction. So if I want to go ahead and find the horizontal distance after 4 seconds, I can just multiply my horizontal speed by that 4 seconds. So to find horizontal distance after 4 seconds, multiply horizontal component of velocity So it seems like we should be going 21.65 feet per second to the right. Ooh, and I'm going to write this ever so slightly differently. I'm trying to do some unit math here. This is 21.65 feet per second to the right times 4 seconds. Seconds and seconds are going to cancel. And that's going to leave us with, we're going to get, rounding a little bit right here, we're going to get 86.6 feet to the right. All right, so notice that what this allowed us to do is it allowed us to sort of strip away the vertical component of motion because we weren't really interested in that. Since our goal in this problem was to only talk about the horizontal component of motion, we decomposed the polar vector into its component form, and then we only used the component that was relevant to the question being asked, which was about the horizontal motion, to answer the question here, right? Again, if you throw a ball at 25 feet per second angled into the air, then your ball is not moving 25 feet per second along the ground. That's not what its horizontal component is. Some of that motion is vertical, some of that motion is horizontal. We extracted both the vertical and the horizontal components from the polar form, and then because this question was specifically about x components, we only used the x component to do our math with at the end right there. We found the horizontal speed that it was traveling at, and therefore horizontal speed in feet per second times 4 seconds gave us the total horizontal distance that this ball traveled. Again, if we're thinking that this ball was following parabolic motion and therefore spending exactly the same amount of time going up as going down, then it should have been going up for 2 seconds and down for 2 seconds. So we could also answer other questions related to this ball throw by saying, and again, we get a little bit, did we throw this ball from the ground or were we standing 5 feet in the air or whatever? But it seems like if the ball went up for 2 seconds, down for 2 seconds, we can see things like the ball went up a total of 25 feet before coming back down 25 feet. And I know that because 12.5 feet per second for 2 seconds is 25 feet, right? And so this is how we can examine things like what angle will give us the optimal distance that an object might end up traveling at out there, things like that. So this angle of our throw, if we can decompose it using our vectors here, then we can use that to help us figure out horizontal and vertical components. So this was our easy example here. I did a lot more work than I needed to do right here. You should notice I could have much more simply just found my x component of my speed and immediately done my multiplication. I did my y stuff here just because I wanted to also, talk about I wanted to be a little bit more long form with this and kind of state all the components of this right here. So I wrote a lot more than was necessary for this guy right here. If you were doing this problem, I'd expect you to write somewhere between a half and a third as much right here. Write your vector and polar as it was given, convert the required component to component form, do the arithmetic with that component. All right. So let's go ahead and look at our last example here. This one will be a little bit more challenging. And this example is associated with static equilibrium. What static equilibrium means is that we have come to rest in a scenario with no motion. Equilibrium means things aren't changing. Static means that there is no motion. Right? So a person would like to suspend a 1,200-pound box from the ceiling. All right, so we're trying to hang something in the garage. Unfortunately, this person only has cable or wires that are rated for 1,000 pounds of tension. Therefore, the person decides to use two different cables to support the box, since maybe that will help distribute the load sufficiently here. The question is, will this work or will this exceed the tension rating? So what we need to do is we need to find the tension in cables A and B. Now, the issue here is that because these cables are at an angle, we can't just straight up look at the amount of force that's being applied to them here, right? So we need to be a little bit more careful. We're going to need to decompose some things um, into their component form right here. So what I want to do is I want to identify several forces in this diagram. First, the force associated with the box. I'll just call this the box force. So my first question to you is, in what direction is this box applying a force? Right? How is this box affecting the cables? Well, what I know is that the box force is going straight down due to gravity, right? So I think I could feel pretty comfortable saying that there is a downward force. Pounds is a measurement of force. So I think I can say that my force associated with the box, I'm going to make this a vector, should be a strictly downward force. So it's only going to get a j component. It should be downward, so it's going to be negative, and the magnitude of it is 1,200. Right? So our box force is a downward force at 1,200 pounds. Right? That's our easy one right there. It's the force that's going in one of our perpendicular directions. Very, very easy to state. The ones that are a little bit more difficult to state here are forces associated with the cables A and B, right? These are the cable forces that we want to identify if these are going to be under 1,000 pounds individually or not to support this 1,200-pound box. Um, so let's look at the force associated with cable A. Now, cable A, the whole point is I don't know what this force looks like. Now, I know that this box is pulling down, right? So what I'm picturing is that the box is pulling towards this dot down here, which means this cable is resisting that, right? That tension force is that opposing motion right here. And so what I'm thinking to myself is that for cable A, we should be getting this as our vector, right? That's the direction the cable is pulling. The cable is pulling to hold the box up right there. This is my force associated with cable A right here. And what I'm thinking to myself is I don't know what FA is, but I am thinking it should have some horizontal and it should have some vertical components here. So I might call this guy, man, I'm just writing the wrong, I'm just typoing all day here. I'm going to call this thing FAX and FAY right here. These are my horizontal and vertical components associated with this. Furthermore, what I know is that since this is a 30-degree angle right here, it seems like this must also be a 30-degree angle. And therefore, there's going to be a 150-degree angle that's opening up over here. Or rather, I should just say this is just a 30-degree angle, or we can think of this as being, right, like 150 degrees from standard position right there. That might be our useful quantity right there. So it seems like we can decompose our A force, which we don't know what it is, to be the magnitude of the A force times the cosine of 150, that's our I component, plus the magnitude of the A cable force times sine of 150, and that's our J component of that force right there. Very, very similarly, we can look at our cable B force, and we're going to get some very similar things as we just got for cable A. Cable B looks like it is being pulled up and to the right at a 45-degree angle. And so I'm going to similarly call this FBX and FBY, right? These are the X and Y components of that pulling that's being done there. And it seems like I can, in general, call my force associated with cable B to be the overall force being experienced by cable B, the magnitude of it, times cosine of 45 I, plus the magnitude of the force associated with cable B times the sine of 45 J. Now, what our issues here are is that we don't know what the magnitudes are for A and for B. So our goal is to find these numbers, FA and FB, in these equations. But the thing that we're sort of stuck at right here is like it's not like I have any direct way to compute them, right? So what we're going to need to do is to figure out what other information do we know about this setup right here. So static equilibrium, what that's trying to convey to us said that there's no overall motion. So there's forces that are being applied, but there's no overall motion. And so if there's no overall motion, what that means to me is this. Now think about this. If I go to push on you and I use 100 pounds of force, and you go to push back on me with 200 pounds of force, you are going to push me backwards because you are applying more force to me than I'm applying to you. However, if you and me both push on each other with the exact same amount of force, then neither of us are going to move. Right? That's because the force in the positive direction is equal to the force in the negative direction, and they cancel out for a net force of 0. On the other hand, with the 100 and the 200 example, if we've got a force 100 units to the right and it's being met by a force 200 units to the left, then the overall force, the net force associated there, will be 100 pounds of force to the left. That's how much more force is being applied to the left than to the right. So the fact that we're in static equilibrium here, the fact that we're just trying to dangle a box with clearly no motion, says that the sum of the forces in the x and y direction should be 0. Otherwise, we'd get motion. Right? So what I'm thinking here is if this box isn't falling, then that must mean that the 1,200-pound force pulling down is being exactly met by a 1,200-pound force pulling up. If there was a more than 1,200-pound force pulling up, then this box would be getting raised, and that's not what's happening. If there was less than a 1,200-pound force pulling up, then this box would be dragging this system downwards. Very, very similarly, the left and the right components must be equal to each other. Otherwise, this box would be swinging to the left or to the right. So it must be that the horizontal components also are going to be summing to 0 in this case right here. So let's go ahead and set up a scenario in which both of those things are happening. Sum of vertical components equals 0. So let's add them all up. What are the vertical components that we have in this scenario here? The 3 vertical components that I have are going to be the 3 things tied to our J terms out here. So it seems like I've got a box force is vertical, and then cable A and cable B both have vertical components. When we get to the horizontal components, it doesn't look like the box is applying any sort of horizontal force. It's just the two cables fighting against one another to the left and the right that we're going to be summing to get 0 out there. So it seems like this should be our F box plus my F sub A x. Oh, that's a horizontal, not x. I meant y. Plus F sub by should be equal to 0. If I add up all of the vertical forces, we should get 0, saying there is no net force in the vertical direction to result in no net motion in the vertical direction here. So what am I going to get in this case right here? It looks like that's going to be negative 1200 for the box force. What's my y component of the A line right here? That should be this term right here. All right, this guy right here, that's my y component of cable A's force. So I'm going to get FA sine of 150. The magnitude of A's force, sine 150. That's also a J component there. Plus, my last one here is going to be the force associated with cable B, but only multiplied by sine of 45 degrees because not all of this force is in the vertical direction right there, right? So we're going to get FB times the sine of 45. That's also a J component there, and that should be equal to 0. So you should notice we can't exactly solve this equation because we have one equation and we have two unknowns right here, which is slightly unhelpful for us. But let's at least go ahead and simplify this guy. One thing that I'm thinking is our goal is just to solve for the FAs. So I'm seeing here that this J vector is not really a useful thing for me here. I'm going to go, because it's just on every single term, I'm going to go ahead and I'm going to add the 1200 to the other side, and let's go ahead and evaluate each of our trig functions here. So I'm getting that the force associated with cable A overall, sine of 150 degrees. When we go sine of 150, that brings us over to here. Sine is measuring my vertical component, and that seems to be the smaller of the two, so I think I'm just getting 1/2. Plus sine of 45 degrees, that should be our root 2 over 2, associated with the magnitude of the B cable's force. And that should be equal to 1200 over here. I'm just trying to see here. I think that's fine. So this is where I'm at sort of with this right here. I summed my vertical forces to get 0, and this is the equation I'm left at. I can't solve for A or B, but so far we've only said that there's no motion vertically. I also know that this box isn't moving, so that means that there's no motion horizontally. So we can set up similar statements here for our X components. So it should be that the sum of horizontal forces is equal to 0 as well, because we're in static equilibrium. So let's also set up equations that say this. Now notice here, there is no box component in the horizontal direction. The box is only pulling straight down. Technically, there's a 0I that goes along with this box vector right here. I just didn't write it because it's 0. All we really need to do is say that the sum of these two vector components right here, the x component each for A and B, if we add those together, we must be getting 0. So it must be the case that our FAX plus our bx is equal to 0 here. So let's go ahead and set up that equation, and then let's see if we can solve this guy. So my two components that I'm looking at right here, that's FAX right there, is the magnitude of the force being experienced by cable A times the cosine of 150. And that's my I component, plus the force being experienced by cable B in magnitude times the cosine of 45. That's also an I component. And those two things have to add to zero. If they didn't add to zero, then this box would be moving left or right, and we said it's not moving left or right. The forces have to go to be equal to each other, one left and one right. Now you should be saying to yourself, how is it left and right if we're getting two positive numbers here? Well, you should recognize that cosine of 150 is not a positive number. Since that is a angle that's in the second quadrant over here, this should be a leftward force right here. So I think I can write this as negative root 3 over 2 times the magnitude of f of a. Cosine of 45 should be plus root 3 over 2 times the magnitude of the force being experienced by cable B. And those should be equal to 0. So my goal is to now solve for the magnitudes associated with cable A and cable B. And it looks like we have a system of equations we can solve. And just because I'm tired of writing all these magnitude symbols, I'm going to write this as 1/2 A plus root 2 over 2B equals 1200. And I'm going to write this as negative root 3 over 2A plus, root 2 over 2. All right, that was my mistake right there. It's a root 2 over 2 for 45-degree angles. Root 2 over 2B. Glad I caught that. So, what do we want to do here? Let's go ahead and, sorry, I'm going to bring my screen down. All right. So to solve these two systems, or to solve the system of two equations, the thing that I'm seeing for myself that's very convenient is it looks like there's a root 2 over 2b in both of these equations. So I'm thinking to myself, let's go ahead and, okay, you know what? Another thing I'm seeing here is that all of these, both sides of these equations have denominators of 2. So let's go ahead and multiply everything by 2 here and just get a equals root 2, a plus root 2b. I'm just clearing some fractions here. Equals 2400. And then over here, negative root 3a plus root 2b equals 0. And I'm thinking, let's go ahead and combine these and use elimination to solve. So I'm thinking a plus root 2b equals 2400. I can go ahead and subtract off negative root 3a plus root 2b equals 0. And what I'm going to do is I'm going to do a big old subtraction problem right here. So I'm doing subtraction. So notice that the whole point of the subtraction is that those two guys are going to cancel. Here I have a minus negative root 3. So this should be a, I'm just going to even write it, minus negative root 3a plus 0 equals 2400 minus 0. Right? So it looks like what we're really getting, how many copies of a do we have? We have a plus root 3a, so one copy of a, an additional root 3 copies of a, so 1 plus root 3a equals 2400. And so it looks like a, which is our shorthand for the total force experienced by cable A, should be 2400 divided by 1 plus root 3. And let's go to our calculator and see what we're going to get here. Or I guess I have that written down in my notes right here. My calculator told me already 878.5 pounds of force. That is the magnitude of force being experienced by cable A. So that's good because remember, let's kind of revisit what we were doing here. Our question was, these cables are really only rated for 1,000 pounds of tension of force. Is this acceptable? Well, it looks like A is all good to go right here. Cable A is only experiencing about 878 pounds of force, which is underneath its force rating. So cable A is safe right here. Let's go ahead and now solve for cable B. So what's up with cable B? Let's go ahead and bring down our equation from up above up there. A plus root 2B equals 2400. We now know that A is this 87 or 878.5 plus root 2B equals 2400. I can go ahead and do my little bit of maths right here. It looks like root 2B is going to be 2400 minus 878.5. So that should be 1615, 22.5. And then divide by root 2. And if we go to our calculator and do this guy, let me make sure I did my subtraction in my head right there correctly. 1522.5 divided by the square root of 2. And I'm getting 1076.57. Did I do my math right? Oh, that's a 1.5 right there. I was like, I feel like I'm off by a smidge right there. And I was. Okay, now let me redo this in my calculator and see if I'm actually getting exactly what my notes say right here. And 1075.86 pounds of force on cable B. This is our total magnitude of force associated with cable B. This is too much. So cable B is not safe. It's greater than the 1,000 pounds that it is rated for right there. So this is kind of our conclusion to this then, is that we found this the forces that both of these cables are experiencing, despite the fact that they're being pulled at angles. The way that we were able to solve this was we said, listen, we know that this system is experiencing static equilibrium, meaning that there's no motion. If we didn't know that, then there's no way for us to have done this problem. We were really required to know that things weren't moving to tell us, therefore, the sum of all of the forces should be equal to 0. It gets really, really, really hairy for us to try and say that the sum of two angled forces, not even at symmetric angles, are going to be equal to 0. Therefore, what we did is we decomposed all of the forces in the problem into being either their horizontal parts or their vertical parts. This sort of brought us into a place where we could make more direct comparisons between them, right? So we then were able to directly compare only the vertical components of the problem and sum them to 0, compare only the horizontal forces in the problem, also sum them to 0, representing the fact that there was no motion. This led us to a system of linear equations, which we were able to solve and show that one of these two cables is bearing about 75 more pounds than it's technically rated for. So this is not an advisable dangling situation from your ceiling garage right here. All right. So these vertical and horizontal component ideas right here, very, very practical, especially in physics, calculus problems like this. But in more generally, I mean, I don't care if you're not going to be a physicist. That doesn't matter. The point here is it's hard to talk about forces going in all different angles and directions like that. And so what we do is we break them down. We decompose them into our component form so that we can just deal with the horizontal parts together, just deal with the vertical parts together. This is our way of breaking down the problem into manageable pieces. And it's very, very often done in vector form right here, right? So recognize that these vectors are a really, really useful way for us to examine forces in directions and stuff like that. So it's certainly the case that this comes up more in physics than in other things, but that doesn't mean that this is like something just for physics right here. This is a general way to think about motion in general. And what I honestly think is that I even think that this baseball problem is probably kind of weird for some of you guys to think about, the fact that when you throw a baseball, even if you know what your speed is, you're probably not measuring your horizontal speed of your throw unless you're like a baseball pitcher that's measuring your speed there. Those are relatively horizontal, but every time you throw a ball at an angle, some of its motion is horizontal, some of its motion is vertical, and the overall velocity that you're experiencing is typically not the thing that you end up sort of measuring. It's usually sort of like how far did it go and how high did it go. Those questions are only asking about what's your x component and what's your y component, and so it matters that we decompose our polar vectors into component form vectors that we can help answer those questions. So this was our introduction to vectors here today. Our important thing was that we got our notation. We saw how to graph vectors and do operations between them. We saw two sort of physics scenarios as to when does it help us to decompose our vectors into their component parts. And importantly, one of the things that we didn't see today was that we didn't see what does it mean to multiply two vectors together. That is going to be the topic that's associated both with the next video as well as the components going into next week. We're going to see that the dot product is one way that we can define multiplication with vector quantities here. It's going to help us define matrix multiplication, and that's what we're going to also spend next week talking about out there. So I'll see you next week for the dot product and our introduction to matrix operations. And again, we're going to come back to see that just like today, we saw this like polar versus rectangular form was kind of a big idea, which is trig topics. We're also going to see that matrix operations, while you guys have if you've taken an algebra class, you've probably seen some matrix operations in algebra. We're going to look specifically at matrix operations that are a little bit more closely tied to trigonometric ideas. We're going to get back to this idea of rotation and how do we implement a rotation in space using a matrix. That's going to be kind of our culminating idea here once we get to our matrices stuff out there. So I will see you guys next week for dot products and matrices. Have a good one.